Hi students, in this video we are going to talk about the probability distributions of the transformations of the random variables. That is, the probability distributions of functions of the random variables. Okay, say we have a random variable x on the probability space omega script of p with probability distribution px. Okay, and y equal to g of x. Y is some function of x. Here, x is some numerical characteristic of an outcome, y is another numerical characteristic of an outcome, which is function of x. Okay. Now, y should be a random variable, right? We can also see this way. Here, x is a function from omega to r, g is a function from r to r. Now, if you look at a composite function, which is g circle x, that is going to be our y. So, our y is function from omega to r. Okay, you should understand g of x as g circle x because x is a function, g is a function. So g of x you need to understand as g circle x, which will be again function from omega to r. So it can be a random variable on this space. Only one technical condition is g should be Borel measurable function. That is, under g, inverse image of a Borel set should be again Borel set for all Borel sets. Then this y will be a random variable according to definition of the random variable. Okay, fine. Now we want to find out. Now we are interested in the probability distribution of y, the py, which is a function from Borel sigma field to r. Okay. Here, idea is to obtain probability distribution of y in terms of probability distribution of x. Question is, how do we do that? Okay. So, for any Borel set B, the py of B means what? Probability of y belongs to B. Here, this P is this P. Okay. Y belongs to be the event in script f because y belongs to B means event in script f which consisting of outcomes in omega for which y omega belongs to B. This is what we mean, which is belongs to script f as y is a random variable on this space. Fine. So now y is what? G of x. That means probability of g of x belongs to B. G of x belongs to B if and only if x belongs to G inverse B. That means the probability of x belongs to G inverse B. Okay. So now the probability of x belongs to G inverse B, G inverse B the Borel set because G is the Borel measurable function. Inverse image of a Borel set should be Borel set. So the probability of x belongs to this Borel set going to be the px of G inverse B. The probability of G inverse B under px. Okay, this is a connection. Okay, so therefore the py of B going to be px of G inverse B. Okay, so this is how we can obtain probability distribution of y in terms of probability distribution of x. This is a connection, general connection. Now, most of the time we work with discrete random variables or continuous random variables. In discrete case, we may have access to PMF of x. Then we want to find out PMF of y. In continuous case, we may have access to PDF of x. Then we want to find out PDF of y. Okay. Next, we want to see connection between PMF of y and PMF of x when we work with a discrete random variables, and connection between PDF of y and PDF of x when we work with a continuous random variables. Okay. Now let us see probability distributions of transformations for discrete type random variables. If x is discrete random variable which support Sx and PMF Px, then y equal to g of x will also be discrete random variable which support Sy consisting of values that g can take over Sx. Now let us try to find PMF of y in terms of PMF of x. For y belongs to Sy, Py of y equal to probability of y taking the value small y, that is probability of g of x taking the value small y. Now saying g of x equal to y is same as g of x belongs to singleton y. G of x belongs to singleton y if and only if x belongs to G inverse singleton y. Okay, so this probability we can write probability of x belongs to G inverse singleton y. Here G inverse singleton y consisting of all preimages of y under G. There could be more than one unless G is 1, 1. Okay, fine. Now this probability of x belongs to G inverse singleton y we can write as Px of G inverse singleton y. Okay, this probability we can write as sum of singleton probabilities under Px, where summation varying over G inverse singleton y. Okay, so next we can write this probability as sum of the singleton x probabilities under Px, where x varying over this G inverse y, which consisting of x in Sx with g of x equal to y. That's why your summation varying over x in Sx with g of x equal to y. Next, the singleton x probability under Px we can write as PMF value at x. So we can write Py of y equal to summation Px of x, where summation varying over x in Sx with g of x equal to y. Okay, so this is how we can find PMF of y in terms of PMF of x. Fine. Further, if G is 1, 1, then G inverse singleton y will be again singleton. That means there will be only one x, which is the preimage of y under G. That single preimage can be denoted by G inverse of y. In that case, in this summation, there will be only one term, that would be Px of G inverse singleton y. Okay, fine. Next, if G is 1, 1 function, then for any y belongs to Sy, Py of y equal to Px of G inverse y. Okay. Example, let us consider a random experiment of tossing a coin with probability of head P until total of R heads obtained. Okay, then the sample space omega consisting of outcomes like this: a1, a2, so on, ax plus r minus 1, ax plus r. Here, each ai is either head or tail. Okay, our experiment always terminate with rth head. So, this ax plus r must be head. Before that, there must be exactly r minus 1 head. So, from a1 to ax plus r minus 1, there must be exactly r minus 1 heads. So, remaining x must be tails. Okay, this is the outcomes will be. Here x is anything from 0, 1, 2, 3, so on, because we may have to see any number of tails before the rth head. Okay, fine. Let us be interested in number of tails before the rth head. Okay, this is our numerical characteristic. For each outcome, we want to assign a number which is number of tails in that outcome. Okay, here x is a random variable which denotes the number of tails before the rth head. Here x can take the value 0, 1, 2, 3, so on. So the support of x will consist of numbers 0, 1, 2, 3, so on. Okay, let us write down PMF of x. Here Px of x is probability of x taking the value small x. Here x equal to x is the event consisting of outcomes in sample space for which the number of tails before the rth head equal to x. Okay, the probability of this event we can write sum of the singleton probabilities like this: summation of probability of singleton omega, where omega running over sample space with x omega equal to x. Fine. Now here in any outcome, number of heads are fixed. Only thing can vary, number of tails. But here the number of tails also fixed to x. So the probability of singleton omega are going to be exactly 1 minus p to the power of x into p to the power of r. Because any outcome in the summation will have r heads and x tails. Only thing is order can change. Okay, then we can use the independence to get this probability. Let me show you typical outcome where we see X tails to see Rth head. Okay, here is the one outcome: head, head, so on, head. These are R minus 1, tail, tail, so on, tail. These are X, end with a head. Okay, this is the one typical outcome. There are X tails and R heads. The probability of this outcome will be by independence. We can assume these trials are independent. Okay, it's going to be P times P times P R minus 1, 1 minus P times 1 minus P, these are X, and into P. So this total is going to be 1 minus P to the power of X into P to the power of R. Okay, so that's why in any outcome with this property we'll have the probability 1 minus P to the power of X, P to the power of R. Okay, so that's why summation each probability going to be 1 minus P to the power of X times P to the power of R, where summation varying over outcome in sample space with X omega equal to X. Okay. Now question is how many outcomes with this property? Okay. Now here this is fixed head. Now here this can vary, right? There must be exactly R minus 1 heads, X tails. Think like a head is like a 1, tail is like a 0. Then this look like a binary string of length X plus R minus 1 with R minus 1 ones. Okay. So we know that there will be X plus R minus 1 choose R minus 1, such a binary string. That's why here we are adding the same term 1 minus P to the power of X times P to the power of R how many times? X plus R minus 1 choose R minus 1 times. So this is going to be X plus R minus 1 choose R minus 1 times 1 minus P to the power of X P to the power of R. Okay. So this is the PMF of X. Okay. Fine. In the next slide, I will write it. So the PMF of X is X plus R minus 1 choose R minus 1, 1 minus P to the power of X times P to the power of R. Okay. For X equal to 0, 1, 2, 3, so on. Okay. This is the PX of X. Okay. Now, let me rewrite this one. We can also express using the extended binomial coefficient. We have a relationship between extended binomial coefficient and ordinary binomial coefficient when the top parameter of extended binomial coefficient is negative number, right? So we can also express this one as like this. Okay, this one we can replace with minus 1 to the power of X minus R choose X, because first of all X plus R minus 1 choose R minus 1, we can write X plus R minus 1 choose X, because we know that n choose R same as n choose n minus R, right? For that reason we can write this. Then we have this relation between, okay, next we have minus R choose X equal to minus 1 to the power of X or plus X minus 1 choose X. That's why this can be replaced with minus 1 to the power of X minus R choose X. So the PMF of X, the PX of X can also be written like this. Okay, minus 1 to the power of X times minus R choose X, 1 minus P to the power of X, P to the power of R. Okay, we can also write this way. Okay, so we can also call this one negative binomial coefficient, this extended binomial coefficient. When top parameter is negative number, we can also call negative binomial coefficient. For that reason, here X is said to have a negative binomial distribution. Okay, these things will come up later. Next. Now y is another random variable which denotes the number of trials required to get the rth head. Number of trials. Okay. So y can be expressed in terms of x like this. Okay. Y equal to x plus r. Y is what? Number of trials, which is where x is number of tails before the rth head, R is the rth head. So total number of trials is going to be number of tails plus number of heads. Okay, x plus r. That's why y can be expressed like this. So here g of x is going to be x plus r. That means y is the function of x. Okay, where g of x equal to x plus r. Now let us try to find PMF of y in terms of PMF of x. Okay, you can also see this is 1 1, right? Now with the support of y, here y can take the value because x can take the value 0 1 2 so on, right? So y can take the value r plus 1 r plus 2 so on, because to see r heads we need at least r trials, right? That's why y can take the value r plus 1 and so on. Okay, now x is going to be what? G inverse y, okay, which is y minus r. Okay, if y equal to x plus r, x is going to be y minus r. What is y minus r? Which is G inverse y. Okay, now PMF of y, since G is 1 1 here, so Py of y simply going to be what? Px of G inverse y. Okay, now what is G inverse y? Which is y minus r. So that is Px of y minus r. Now we already know PMF of x, which is what? Px of x equal to what? X plus r minus 1 choose r minus 1 into 1 minus p to the power of x, p to the power of r. Okay. Now simply let us replace x with a y minus r now. Now what we get? Py of y equal to y minus r plus r minus 1 choose r minus 1, 1 minus p to the power of, we are replacing x with y minus r into p to the power of r. So now here this r cancel. Okay, we will end up with y minus 1 choose r minus 1, 1 minus p to the power of y minus r, p to the power of r. Here y vary from r plus 1 and so on. This is going to be PMF of y. Okay. Next. So the Py of y is y minus 1 choose r minus 1, 1 minus p to the power of y minus r times p to the power of r. Y varies from r plus 1 so on. Okay. This is the PMF of y which we obtain in terms of PMF of x. Okay. Fine. In this example, we have used the transformation y equal g of x, which is 1 1, to find the PMF of y in terms of PMF of x. In the next example, we are going to use the transformation y equal g of x, which is not 1 1. Then we will find the PMF of y in terms of PMF of x. Okay. Example: x be a discrete random variable which support fx consisting of numbers 1, 2, 3, 4, so on, and the PMF px of x equal to 1 by 2 to the power of x for x equal to 1, 2, 3, so on. Now let us take the transformation y equal to x minus 2 whole square. That is, g of x is what here? X minus 2 whole square, which is not going to be 1, 1, because under this mapping 1 and 3 both go to 1. Okay, because you see g of 1 is what? 1 minus 2 whole square, which is going to be 1, and g of 3 also going to be 1, because 3 minus 2 whole square, which is also 1. Here 1 and 3 both are mapping to 1, so that's why we can say that g is not 1 1 here. Okay. Here the support of y, that y can take the values 0, 1, 4, 9, 16. It can take only squares, right? X minus 2 whole square. Okay. So fine. In this mapping from Sx to Sy, only one having two preimages. Everything else will have only single preimage. Let me show you. Here is the Sx, which is 1, 2, 3, 4, 5, 6, and so on. Here is Sy, 0, 1, 4, 9, 16, 25, and so on. Okay. Here, inverse image of 0 is 2. Only 2 go to 0, because 2 minus 2 whole square is what? 0. Okay. That is g of 2 is what? 0. Okay. And inverse image of 1 is 1 and 3. This 1 and 3, okay, both go to 1. And inverse image of 4 is going to be 4 because g of 4 is what? 4 minus 2 whole square, which is 2 square, which is 4. Okay, that's why inverse image of 4 is 4. Inverse image of 9 is 5 because g of 5 is what? 5 minus 2 whole square, which is 3 square, which is 9. So 5 go to 9. Similarly, inverse image of 16 is 6 because g of 6 is going to be 6 minus 2 whole square, which is 4 square, which is 16. Okay, like that everything else will have a only unique preimage. Only one will have a two preimages. Fine. Now in general, for any y bigger than or equal to 4, okay, the preimage is going to be this. Okay, g of x equal to y means what? X minus 2 whole square equal to y, that is x minus 2 equal to root y, that is x equal to root y plus 2. That is a single preimage, which is g inverse of y. Okay. So therefore, now let us write down PMF of y in terms of PMF of x. We know that Py of y is what? Let me clear this. Now the PMF of y, Py of y equal to Px of g inverse singleton y. Here, Px of g inverse singleton y is going to be sum of the PMF values at x, where x varying over this g inverse singleton y. Okay. When y equal to 0, the g inverse y consisting of single element. That's why in the summation we have only one term, that is the g inverse 0 is what? Only 2. Okay, that's why in the summation we have only one term, that is px of 2. When y equal to 1, the g inverse of singleton 1 consisting of only two elements, 1 and 3. That's why in the summation we have only two terms, that is px of 1 plus px of 3. Okay. From y greater than or equal to 4 onwards, g inverse singleton y consisting of only one element, that is root y plus 2. Okay. That's why in the summation we have only one term, that is px of root y plus 2. Now the px of 2 is what? Here px of x is 1 by 2 to the power of x. So this is going to be 1 by 2 to the power of 2, which is 1 by 4. Here px of 1 is 1 by 2 to the power of 1 plus px of 3 is 1 by 2 to the power of 3. Okay, that is 1 by 2 plus 1 by 8, which is going to be 5 by 8. Now this is going to be 1 by 2 to the power of root y plus 2. That is 1 by 4 times 1 by 2 to the power of root y. Okay. This is the PMF of y. When y equal to 0, we got a 1 by 4. When y equal to 1, we got a 5 by 8. From y equal to 4, 9 onwards, Py of y equal to 1 by 4 times 1 by 2 power root y. Okay. Let me clear this. So this is our PMF of y. Okay. When y equal to 0, 1 by 4. When y equal to 1, 5 by 8. From y equal to 4, 9, 16 onwards, the Py of y value 1 by 4 times 1 by 2 power root y. Okay. So this is the PMF of y that we obtain in terms of PMF of x. Okay. Fine. Next problem. Let x be a discrete random variable with the PMF values at -1, 1 by 3, at 0, 1 by 4, at 1, 5 by 12. It's perfectly going to be valid PMF. As you can see, all are positive and the sum will add up to 1. So it's a valid PMF. And y equal to x square, then find the PMF of y. Okay. Here first of all, the support of x is -1, 0 and 1. Okay. and the transformation is y equal to x square, that is g of x equal to x square, which is not going to be 1 1. As you can see, minus 1 square and 1 square will be same, so g is not 1 1. And the support of y, here y will take the value 0 and 1. Okay, now we know that py of y is going to be what? Px of g inverse singleton y, which is going to be sum of PMF values at x, where x varying over g inverse singleton y. Now here y can take the value 0 and 1, so g inverse singleton 0 going to be only 0, and g inverse singleton 1 going to be, here both 1 and minus 1 can map to 1, because 1 square is 1, minus 1 square also 1. Okay, so now let us try to find out PMF values of y for 0 and 1. Okay, now py of 0 is going to be what? Px of g inverse singleton 0, but g inverse singleton 0 having only 0, so in the summation we have only one term, that is px of 0, that is 1 by 4. Okay, so that's why py of 0 equal to 1 by 4. Similarly, py of 1 is what? Px of g inverse 1. In g inverse 1, we have two candidates here. So in the summation, we'll have two terms, that is px of minus 1 plus px of 1. So px of minus 1 plus px of 1. So px of minus 1 is 1 by 3 and px of 1 is 5 by 12. They add up to 3 by 4. Okay, so therefore py of 0 value 1 by 4, py of 1 value 3 by 4. So we got the PMF for y. Okay, because y take the only two values 0 and 1, so we got it. So therefore py of 0 1 by 4 and py of 1 is 3 by 4. This is the PMF of y. Fine. Now let us see probability distributions of transformations for continuous type random variables. Okay, let x be a continuous random variable with a PDF small f of x, and we have a transformation y equal to g of x. Then we want to find PDF of y in terms of PDF of x. One way is first somehow get the CDF of y, then differentiate it to get the PDF of y. Okay, let's try to find out CDF of y first. CDF of y, Fy of y equal to, by definition, probability of y less than or equal to y. Okay, so that means this is the probability of interval minus infinity to close y under py. And we have a relationship between probability distribution of y and probability distribution of x. That is py of b equal to px of g inverse b for all Borel sets. This is the relationship between probability distribution of y and probability distribution of x. So in particular, for this b also it should be what? Px of g inverse interval minus infinity to close y. Okay, and we can get probability of any Borel set under px once we have access to PDF of x. That is px of b for any Borel set going to be simply integral of PDF over that Borel set. Okay, this is how we can get probability of any Borel set under px using PDF of x, simply integrating the PDF over the Borel set b. Okay, in particular for this Borel set also it should be what? Integral of PDF over this Borel set g inverse interval minus infinity to close y. Okay, this is how we can get CDF of y in terms of PDF of x. Once you get the CDF, you can differentiate it to get the PDF of y. So the PDF of y is going to be derivative of CDF of y. Okay, you simply differentiate CDF of y, you get the PDF of y. Fine. Let x be a continuous random variable with a PDF small f of x and CDF capital F of x, and we have a transformation y equal to x square Then let's try to find out CDF of y first, then PDF of y. Okay, CDF of y. For y less than 0, CDF value at y is what? Probability of y less than or equal to y. This is going to be 0 because y equal to x square, right, which is non-negative. So y will never take the negative value. So y less than or equal to y will never happen. So the probability of y less than or equal to y is going to be 0 in this case. Okay. If y greater than or equal to 0, then Fy of y is what? Probability of y less than or equal to y. What is y? X square. That means probability of x square less than or equal to y. X square less than or equal to y if and only if mod x less than or equal to root y. So this probability is going to be same as probability of mod x less than or equal to root y. Mod x less than or equal to root y means x is between minus root y to root y. Okay, so this look like a probability of a less than or equal to x less than or equal to b. Okay, we know how to answer this one. So if you want to use CDF, you can answer this one as like f of b minus f of a. If you want to use PDF, then you can answer this one as integration of this PDF from a to b. Okay, so we can do it in two ways. So the CDF of y is going to be 0 when y less than 0. When y greater than or equal to 0, this probability is going to be in terms of CDF fx of root y minus fx of minus root y. Okay, because it should be f of b minus f of a, right? Here a is minus root y, b is root y. Okay, if you want to use PDF, what you do, you have to integrate PDF from minus root y to root y. Okay, this is another way you can get the CDF. Okay, now if you differentiate it, let me clear this. Now let us differentiate the CDF to get the PDF. Okay, let's use this part. Okay, PDF of y going to be derivative of the CDF of y. So we're going to differentiate. If you differentiate 0, you will get 0 is a constant. So when y less than 0, still the derivative of 0 going to be 0. When y greater than or equal 0, the derivative of this, okay, now, so derivative of the sum going to be sum of the derivative. So u plus v method. So derivative of fx root y minus derivative of fx minus root y. Okay, now again, now we apply chain rule. First of all, derivative of the capital F going to be small f, derivative of the CDF going to be PDF, right? So it's going to be fx of root y. By chain rule, we need to differentiate root y. Okay, it's going to be 1 by 2 root y. Okay, minus. Okay, again here also fx minus root y. By chain rule, we need to differentiate minus root y. It's going to be minus 1 by 2 root y. Okay, so minus into minus plus, so we end up with a fx root y plus fx minus root y by 2 root y. Okay, so that's what we'll get next. So when y less than 0, this is 0. Now if you differentiate this, we end up with, okay, fx of root y by chain rule. I just did this here. Okay, in the next step, we will end up with this. Okay, fx root y plus fx minus root y by 2 root y when y greater than or equal to 0. When y less than 0, you have a 0. Further, if you happen to know that f is even function, that is, if you see that f of minus x same as f of x, that means if graph of PDF is symmetric with respect to y-axis, then we say even function. That is, f of minus x should be equal to f of x. In that case, these two will be same, so they get added. So we will get 2 fx root y by 2 root y. These 2 cancel. You will end up with fx root y by root y. This will be simplified to simply fx root y by root y in that case. Okay. Next, so if f is even function, that is f of minus x equal to f of x, so we have pdf of y equal to 0 when y less than 0, fx of root y by root y when y greater than or equal to 0. When we have our transformation y equal to x square. Okay, this is the thing. Okay, problem. Let x be a continuous random variable with a CDF capital F of x equal to 0 for x less than 0, x square for 0 less than or equal to x less than 1, 1 for x greater than or equal to 1. Find the PDF of y equal to x square. Here our transformation is y equal to x square. We have to find PDF of y. Okay. First let us try to find CDF of y. Then we differentiate it to get the PDF of y. Okay. First CDF of y. We already seen from above result writing CDF of y in terms of CDF of x. Okay. Fy of y going to be 0 for y less than 0. For y greater than or equal to 0, it's going to be fx of root y minus fx of minus root y. Okay. Let's try to use it to get the CDF of y. For 0 less than or equal to y less than 1, root y also between closed 0 open 1. So fy of y value fx root y minus fx minus root y, as root y is between closed 0 open 1, so we have to use this function here. Fx of root y going to be root y whole square, and minus root y going to be negative, so when x is negative, f of x value is 0, so it's going to be 0. This is going to be 0, this is going to be root y whole square, so we get y. Now, for y greater than or equal to 1, root y also will be greater than or equal to 1. Okay. Then fy of y value fx root y minus fx of minus root y. As root y greater than or equal to 1, we know that CDF of x, okay, is going to be 1 for x greater than or equal to 1. So here we have to use 1. Okay. But minus root y is going to be negative. When it is negative, CDF value is 0. So here we have to use 0. 1 minus 0 going to be 1. Okay, fine. So therefore CDF of y is 0 for y less than 0, y for 0 less than or equal to y less than 1, 1 for y greater than or equal to 1. Okay, this is our CDF of y. Now if you differentiate it, you will get the PDF of y. Okay, as you can see, outside 0 and 1, function is constant, so the derivative going to be 0. So between 0 and 1, the function is y, the derivative with respect to y is going to be 1. So the PDF of y is going to be derivative of CDF of y with respect to y. It's going to be 1 between 0 and 1, 0 otherwise. Okay. Here the random variable y is said to have uniform distribution over the interval 0, 1. Okay. Fine. Okay, problem. Let x be a continuous random variable with a PDF small f of x equal to 1 by 2 for minus 1 less than x less than 1, 0 otherwise. Then find the PDF of y equal to x square. Again our transformation is y equal to x square. This time we are given PDF of x. Okay. So now again we are going to find first CDF of y, but this time we will use PDF of x. Then we will differentiate CDF of y to get the PDF of y. Okay. First of all, the support of x is, we can see, interval minus 1 to 1. For the transformation y equal to x square, the CDF of y in terms of PDF of x is this. Okay. Fy of y equal to 0 for y less than 0. For y greater than or equal to 0, integral of the PDF from minus root y to root y. Okay. This is what CDF of y. Now for 0 less than or equal to y less than 1, we can see that root y is between 0 and 1, minus root y is between minus 1 and 0. That implies we can see that minus 1 less than minus root y less than or equal to 0 less than or equal to root y less than 1. That means minus root y and root y are also between minus 1 and 1. Okay, so in that case, so as y greater than or equal 0, we have to use this integral to find out CDF value at y. So fy of y going to be minus root y to root y, but I'm going to use f of x equal 1 by 2 as minus root y and root y between minus 1 and 1. So integrand I'm going to use of. Okay, if you integrate it, you will end up with root y, because the integral of 1 by 2 going to be x by 2. The limits are minus root y to root y. If you apply the limits, root y by 2 minus root y by 2. Okay, it's going to be minus into minus plus 2 root y by 2. You will end up with root y. Okay, so this is the root y. Fine. Fy of y equal root y when 0 less than or equal to y less than 1. Fine. Now, for y greater than or equal to 1, we can see that root y is greater than or equal to 1 and minus root y less than or equal to minus 1. So, the integral minus root y to root y f of x dx we can break into three parts: minus root y to minus 1 and minus 1 to 1 and 1 to root y. As we can see that the support of x is minus 1 to 1, outside minus 1 to 1 the PDF going to be 0, so integrand going to be 0 from minus root y to minus 1 and 1 to root y. So only thing is we have to work out this one, that will become 1. Okay, so integral from minus 1 to 1 of dx going to be what? X by 2 minus 1 to 1. It's going to be 1 by 2 minus 1 by 2. It's going to be 1 by 2 plus 1 by 2. That is going to be 1. Okay, so fy of y going to be 1 for y greater than or equal to 1. Therefore, our CDF of y is 0 when y less than 0. For 0 less than or equal to y less than 1, the CDF value is root y. For y greater than or equal to 1, this is 1. Okay, this is the CDF of y. Now, if you differentiate it, as you can see outside 0, 1, the CDF is constant, the derivative going to be 0. So, between 0 and 1, it is root y. Derivative of the root y is going to be 1 by 2 root y. So, the PDF of y, fy of y is going to be derivative of the CDF, which is going to be 1 by 2 root y between 0 and 1, 0 otherwise. Fine? Okay. This is the PDF of y. Okay. Okay, problem. Let x is a continuous random variable with a PDF small f of x equal to 1 by root 2 pi e power minus x square by 2 for minus infinity less than x less than infinity. Then find the PDF of y equal to x square. Again, our transformation is y equal to x square. This time, let's find the PDF of y directly in terms of PDF of x without finding CDF of y. We have one result, let's use this time. In fact, we can also see that given PDF is even function. That is, we can see that f of minus x same as f of x. In that case, we have much simpler result. One note here, the random variable with this PDF is said to have something called standard normal distribution. We have some name for this distribution, standard normal distribution. They will come up later. I'm just introducing names here. Okay, fine. Now, here we can see that support of x is interval minus infinity to infinity, and we can also see that the PDF is even function. In that case, For this transformation, PDF of y equal to 0 when y less than 0. For y greater than or equal to 0, we have fx root y by root y. Okay. For y less than 0, this is 0 fixed. Now let us see what is this fx root y by root y. Okay. Now here fx root y by root y, the numerator, simply we are replacing x with a root y in fx of x, which is what? 1 by root 2 pi e power minus x square by 2. That's it. So 1 by root 2 pi e power minus root y whole square by 2 by root y. Okay. This is going to be, I can write 1 by root 2 pi y e power minus y by 2. Next, I can write 1 by root pi 1 by 2 y by 2 power 1 by 2 minus 1. Feel free to check this. The whole thing gets simplified to this one. 1 by root 2 pi y. Okay. And into e power minus y by 2. Okay. So now you should know one thing about gamma function, that is gamma of value is root pi. If you don't know anything about gamma function, please read about gamma function. Okay, they will come up again later. Fine. Now, so now we can see the whole thing I wrote. The whole thing got simplified to 1 by root pi half into y by 2 power 1 by 2 minus 1 e power minus y by 2. Okay. Now let's put it in numerator and the root pi in the denominator with gamma of. So I can write of y by 2 power 1 by 2 minus 1 e power minus y by 2 by gamma of. Okay, since gamma of value root pi. Okay, so therefore our PDF of y is going to be what? Fy of y is 0 for y less than 0. When y greater than or equal 0, that Fy of root y by root y got simplified to this 1 by 2 y by 2 power of minus 1 e power minus y by 2 by gamma of. Okay, there is the one reason I put it in this way. Okay, it's going to be more general distribution. This particular one have a name, that is something called chi-square distribution. Chi-square distribution with 1 degree of freedom. Okay, fine. Okay, so these things will come up later. We will study in details. Okay, in general, what is the chi-square distribution with n degree of freedom? This is one special one which we call chi-square distribution with 1 degree of freedom. Okay, fine. Okay, theorem. Let x be a continuous random variable with a PDF small fx of x and support sx. And here we have a transformation y equal to g of x, where g is one differentiable function on support of x. Then the PDF of y is given by fy of y equal to fx of g inverse y modulus of derivative of g inverse y with respect to y. For y belongs to support of y, which consisting of values that g can take over sx. Okay. Here, whenever we have a transformation y equal g of x, where g is one differentiable function on sx, then PDF of y can be obtained like this. Okay, fy of y equal to fx of g inverse y modulus of derivative of g inverse y with respect to y. Okay, this is how we can obtain PDF of y. Okay, let's prove this. Proof. Here g is one function. That means g should be either strictly increasing or strictly decreasing. So we are going to show it in two cases. In both cases, what we do, we first find CDF of y, then we will differentiate it to get the PDF of y. Okay. Case 1. Case 1 is G is strictly increasing. In this case, let us find the CDF of Y and differentiate it to get the PDF of Y. Okay. So CDF of Y equal to what? Fi of Y, which is probability of Y less than or equal to Y. Y is G of X, so which is probability of G of X less than or equal to Y. You should know one thing. G is strictly increasing if and only if G inverse strictly increasing. At least you can check in terms of derivative. Okay, derivative of G is positive if and only if derivative of G inverse is positive. Okay, feel free to check that. Now if I take G inverse both sides, still we will have a same inequality. So the probability of G inverse of G of X less than or equal to G inverse of Y, because G inverse also strictly increasing. Okay. Now G inverse of G of X means X, so it's going to be probability of X less than or equal to G inverse Y. Okay. By definition of CDF of X, okay, so it's exactly fx of G inverse Y. Okay. Now we got a relationship between CDF of Y and CDF of X. So therefore we have Fi of Y equal to fx of G inverse Y. Now PDF of Y, small fi of Y is derivative of CDF of Y. Okay. So that is derivative of the right hand side d by dy of fx of G inverse Y. Okay. Now let us differentiate using the chain rule. Now by chain rule we can write the right hand side derivative is fx of G inverse Y, because derivative of capital Fx is small fx, derivative of the CDF is PDF, right? So it's going to be fx of G inverse Y. By chain rule we need to differentiate G inverse Y. That's going to be derivative of G inverse Y with respect to dy. Okay, fine. Now this is the PDF of Y we got. Now we should know one thing. When G inverse is strictly increasing, derivative of G inverse going to be positive, strictly positive. So it's okay to put a modulus here. Okay, so that's why in the next step, as you know, derivative of G inverse Y going to be positive when G inverse is strictly increasing. So we can write Fi of Y equal to fx G inverse Y times modulus of derivative of G inverse Y by dy. Because anyway it is positive, it's okay to put modulus, no problem. Okay, so fine. Next, case 2. Case 2, G of X is strictly decreasing. Okay, in this case, again let us find the CDF of Y, then differentiate it to get the PDF of Y. Okay, now CDF of Y, Fi of Y equal to probability of Y less than or equal to Y. Again, Y is what? G of X less than or equal to Y. Again, if G is strictly decreasing, if and only if G inverse also strictly decreasing. You can verify through derivatives, because derivative of G negative if and only if derivative of G inverse will be negative. Okay. If I take G inverse both sides, inequality will be reversed like this. Probability of G inverse of G of X will be greater than or equal to G inverse of Y. See, inequality got reversed as we apply G inverse, which is strictly decreasing function. That's why in the next step we will write probability of G inverse of G of X greater than or equal to G inverse Y. Okay, as you know, G is strictly decreasing if and only if G inverse is strictly decreasing. Now this is nothing but X. So probability of X greater than or equal to G inverse Y, which we can write 1 minus probability of X strictly less than G inverse Y, because probability of E going to be 1 minus probability of E complement, right? That's why. For a continuous random variable, whether we include endpoints or not, the probability will be same. That's why we can also take the probability of X strictly less than G inverse Y will be same as probability of X less than or equal to G inverse Y. Now this we can take as fx of g inverse y. Okay, now this we can write 1 minus fx of g inverse y. Okay, so now, so therefore CDF of y, fy of y equal to 1 minus fx of g inverse y. Here the PDF of y going to be derivative of the CDF of y. And the right hand side derivative going to be derivative of 1 minus fx of g inverse y. If you do the derivative for this, derivative of 1 going to be 0. Now we have to do the derivative of this. Now in the next step we will apply chain rule. So the derivative of this is going to be fx of g inverse y, because derivative of CDF is PDF. Okay, and by chain rule we need to differentiate g inverse y. That's going to be derivative of g inverse y with respect to y. Okay, fine. Now since g inverse is decreasing, so derivative of g inverse y by dy is going to be negative. Okay, and this minus and this negative. Okay, this is negative and we have a minus. Both we can put together and put a modulus of like a derivative of g inverse y by dy. Okay, we'll do that next. Okay, so we are getting rid of this minus and we put a modulus here. So fy of y going to be fx of g inverse y mod derivative of g inverse y with respect to dy for y belongs to sy. Okay, so in both cases we end up with the same expression for PDF of y. Okay, so this is how we can obtain PDF of y in terms of PDF of x when g is one differentiable function. Okay, this is the thing. Okay, here the derivative d of g inverse y by dy is called one variable Jacobian of inverse transformation x equal to g inverse y. Okay, fine. Okay, problem. Let x be a continuous random variable with a PDF small f of x equal to 1 for 0 less than x less than 1, 0 otherwise. Then find the PDF of y equal to minus 2 log x. Here our transformation is y equal to minus 2 log x, which is going to be 1 differentiable function, 1 differentiable function. So we can use above theorem to find out PDF of y. Okay, so first of all we can see that support of x is open interval 0 to 1 and we have a transformation y equal to minus 2 log x. Okay, so here g of x is minus 2 log x. Let's try to find out g inverse y. Okay, so here y equal to minus 2 log x means if and only if log x equal to minus y by 2 if and only if x equal to e power minus y by 2. Okay, that's why that inverse function g inverse y is going to be e power minus y by 2, that is x. Okay, also if x between 0 to 1, that is what is x, e power minus y by 2 between 0 to 1, if and only if y is from 0 to infinity. Okay, so therefore, so here we can see that 0 less than or equal to y less than infinity if and only if 0 less than e power minus y by 2 less than 1, which is nothing but x. Now the support of y is going to be the values that g can take on the support of x. Okay, as you know, x varies from 0 to 1, y varies from closer 0 to infinity. That's why the support of y is going to be closer 0 to infinity. Fine. Now let's look at the Jacobian of the inverse transformation x equal to g inverse y, which is derivative of g inverse y. Okay. Next, the derivative of g inverse y with respect to y is going to be minus 1 by 2 e power minus y by 2, because g inverse y is what? E power minus y by 2. The derivative of g inverse y with respect to y going to be
minus 1 by 2 e power minus y by 2.
okay, this is the one variable Jacobian of inverse transformation x equal to g inverse y. Fine. Now the PDF of y is what? Fy of y equal to fx of g inverse y. This g inverse y is e power minus y by 2. Okay. And as we know, y come from interval 0 to infinity if and only if e power minus y by 2 come from 0 to 1. Okay. That means, so this e power minus y by 2, as y belongs to sy, which is 0 to infinity, this e power minus y by 2 come from between 0 to 1, then the PDF value is going to be 1. This is going to be 1. Okay. And in the next step, 1 times modulus of the Jacobian, which is minus 1 by 2 e power minus y by 2. Therefore, Fy of y equal to half e power minus y by 2 when y greater than or equal to 0, 0 when y less than 0. Okay. So, this is the PDF of y. Here, y is said to have exponential distribution with rate parameter lambda equal to 1 by 2. We will see this distribution later in detail. Okay. Problem. Let x be a continuous random variable with a PDF f of x equal to 1 by pi for minus pi by 2 less than x less than pi by 2, 0 otherwise. Then find the PDF of y equal to tan x. Here our transformation is y equal to tan x. Okay. First of all, we can see that the support of x is open interval minus pi by 2 pi by 2. Okay. Sx is open interval minus pi by 2 to pi by 2. Transformation is y equal to tan x. So immediately we can see that support of y will be interval minus infinity to infinity, because as x varies from minus pi by 2 to pi by 2, the tan x take the values from minus infinity to infinity. So it's pretty clear. Here now, the tan x function is 1 function on interval minus pi by 2 to pi by 2. Okay. Of course, it is differentiable function. So here g of x equal to tan x is 1 differentiable function on sx. What is sx? Minus pi by 2 to pi by 2. So from the interval minus pi by 2 to pi by 2, tan x is in fact 1. Okay. Of course, it is differentiable function. So we can apply above theorem to find out the PDF of y. Okay. So let us see what is the g inverse y. Okay. First, now for y equal to tan x, g inverse y is going to be tan inverse y. Now, as y come from minus infinity to infinity, tan inverse y come from minus pi by 2 to pi by 2. Okay, fine. Now, how do you get the PDF of y? PDF of y is what? Fx of g inverse y and modulus of the Jacobian, which is derivative of g inverse y. Okay. Here what is the fx of x? 1 by pi for x between minus pi by 2 pi by 2, 0 otherwise. Okay. So fine. Now next, fy of y equal to fx g inverse y modulus of the Jacobian derivative of g inverse y by dy. Now what is g inverse y? But here support of y is minus infinity to infinity. So as y come from minus infinity to infinity, the g inverse y is tan inverse y. It's come from minus pi by 2 to pi by 2. So the PDF value going to be 1 by pi here. So it's going to be 1 by pi. Then the derivative of tan inverse y is going to be 1 by 1 plus y square. So in the next step we will write this replaced with 1 by pi. The derivative of tan inverse y with respect to y is going to be 1 by 1 plus y square. So you don't have to put modulus because 1 plus y square anyway non-negative. So in the next step, so now fy of y equal to 1 by pi times 1 by 1 plus y square for minus infinity less than y less than infinity. Here y is said to have Cauchy distribution. Okay, fine. Okay, let me stop now. Thank you.